Hi, this is Mr. Yeager with physics. We're introducing waves today, waves. And so what we're seeing here is, or what we're going to look at or introduce is basically what are waves, all right, what do they carry? And then we're going to break them down. What types of waves are out there? How do we classify them? And then even within that, how do they move? There's two different versions in terms of ways that they move. A lot of terminology with this one, not much math. We will end with the big wave formula. There's only one, but that's what we're going to end with on this pretty long PowerPoint as we go through it. So, obviously you can see my nice ocean waves moving along right there. So, first off, what is a wave itself? Okay, a wave is this vibration or disturbance in space. All right, it is a movement of a vibration through space, and in particular, hopefully my pen does not keep on leaving me constantly during this lecture, but the main thing is a wave will carry energy. All right, a wave carries energy, all right, over a distance through space. All right, now it is possible that the wave has to travel through what's called a medium, through an actual substance. Obviously, like the last one, it could be traveling through water. That water would be called the medium. Sound is carried by the air. That would be the medium, the gas molecules in the air. But not all waves need a medium. So there is no rule that says it must have a medium. A wave itself must be just simply a regular disturbance or a consistent vibration that is carrying energy over a distance. All right. So this is going to pop up a couple times. There's a couple different places where in the classroom I then show a couple of videos. I'll let you go back. If you look at the PowerPoint itself, you can look at these specific, obviously, examples of wave motions. One's just showing basically ocean waves. Another one showing basically sound waves. Okay, trying to get a visual of those. All right. So there are primarily two types of waves out there. The funny thing is this bottom one, matter waves, we really don't use too much. So let's look at the top one. The first category of wave is what we call a mechanical wave. And we call it a mechanical wave because it requires a medium. There must be something carrying that energy. If it is carried through a medium, that is a mechanical wave, all right? Or if it requires, in order for that wave to move, it requires a medium to be there, that is a mechanical wave. So we will learn that water, and more importantly sound, are going to be our primary, our sound especially, our primary mechanical wave that we're interested in, okay? Our second one is the electromagnetic wave. So the only two we're really interested in is mechanical and electromagnetic. Electromagnetic, well, those are waves that don't need a medium. So that's not hopefully too difficult of a definition. One requires a medium. Guess what? The one that starts with an M needs a medium. Then we have electromagnetic. It does not need a medium. Electromagnetic are much more specific. They are specifically light waves and any version of light off of the electromagnetic spectrum. Right? Radio, X, gamma, infrared, microwave. What am I missing? Did I say infrared? I think I did already. Ultraviolet. So those would be the forms of electromagnetic. All right. So again, we kind of keep repeating certain things. A wave itself can either be mechanical or electromagnetic. It is simply traveling through space and carrying energy from one place to another. All right. Now, underneath this categories of mechanical and electromagnetic waves. This is basically how they will travel. All right, there's two types, I should say now, of traveling for the waves. And again, I bet you recognize some of these. At least you'll recognize what transverse is. They are either what we call transverse waves. These are the classic ocean waves, the up and down motion. If you see me in my classroom, I'm moving my hand up and down in basically that classic wave motion. All right. Longitudinal we'll see is much more like a pumping motion, where it pulls air in and pushes it back out, pulls air in and pushes it back out. So those are our two main types, and you're going to see lots of pictures of what I mean by this. So what we are going to see is that when we have a mechanical wave can either move through a transverse manner or a longitudinal manner. It turns out electromagnetic only travels as transverse. So, this is how a transverse wave looks. The definition is that the oscillation itself is perpendicular to the direction of motion. So this wave, as you can see in the diagram, the energy is moving left to right, but as it moves through it, it creates this up and down motion, the classic wave motion going up and down as it travels across, all right, or as it travels down. It doesn't have to; it could just stay up this whole thing could just keep on lifting the spring upwards, but that would be transverse because that is perpendicular to the direction of motion. Okay, that is a transverse wave. That's the one I think most of you guys already probably know. All right, the names of these things. Obviously, we need to name the parts. The high points on the transverse wave is called the crest. The bottom part is called the trough. Make sure you at least know the names in case you get some simple questions going. What's the high point? What's the low point? Or obviously mentioned in the question itself. So if we label everything, if we go through, where's the crest? The crests are going to be up at the top. The troughs are going to be down at the bottom. This is going to lead us to a couple other, obviously, definitions. Okay, we can look at amplitude. All right, which we talked. If you're in the AP class, we talked a little bit about with simple harmonic motion. This is a version of simple harmonic motion. All right, and the amplitude is either considered the height or the depth of the wave itself. How high or below what we call the equilibrium point. Okay, the equilibrium point. As you keep on seeing me switch back and forth, get my pen back. All right. So, I bet you I'm going to lose it again. Yep, there it goes. Let's see if I can get this. All right, I'll just write it next to it. This line in the middle would be simply called the equilibrium point, or sometimes called the resting point. It's basically trying to say, where does the wave have where is the wave not displaced at all? Where is the wave not displaced at all? That would be the equilibrium point, all right? And so this obviously is, again, the transverse wave. When we measure the amplitude, we're measuring it up from the equilibrium point up, or from the equilibrium point to the trough, all right? The waves we basically do will essentially stay the same size for the most part. It's again simple harmonic motion. We're not going to lose or gain any energy, at least initially. Obviously, the biggest mistake some people do with amplitude, they measure from crest all the way down to trough. That is incorrect. That is not amplitude. Okay, that is not amplitude. So it's only halfway between those 2 points. Okay, excuse me. As for wavelength, the classic definition is crest to crest, trough to trough. What we need to make sure we understand is we need to make sure one wavelength is one complete wave. That means it's one complete up and down motion of the wave itself. We're going to have to make sure we can see these waves, because this is not always going to be the way that the waves are drawn. It might start at the very top and obviously then oscillate from the very top all the way to the bottom and back up again. We need to pick out one point on a wave to be able to figure out the wavelength and come back to that exact same point. All right, that's something I know some people get tripped up on. Longitudinal waves. For longitudinal waves, this is where the oscillation is now in the same direction as the wave moves. So this, a good example here is with the slinky. When you pull it in, compress it, and then release it, it'll create that compression and what we're going to call a rarefaction as it travels down. So the oscillation, this slinky actually bounces back and forth as it travels down. We just see it go bump, 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 bump. The energy's traveling like this down the slinky. All right, that's what we're looking for. Oh, so there's an example. Here's a little animation of that. All right, you can go here and basically look at some of the other examples of longitudinal and transverse waves. Quick question. To create a wave, you need to create a disturbance, or sometimes we call a pulse, and that energy is then transferred down to the next coil. Here's another good look at a longitudinal wave. All right, Now this shows one other major point, okay? That I mean, I think people get confused on. This is almost like an optical illusion. I think people think that obviously we actually have this traveling of the particles all the way down this tube here. The thing is, waves carry energy, not matter. Waves carry energy, not matter. If you actually focus on one single dot, you'll see that that dot, all it does is just go back and forth, back and forth, back and forth. All right? That's because this is a collision happening. To move that energy, one particle must hit another particle, and then it will bounce back. And this continues on and on and on as long as we have this regular disturbance from the red bar on the side. So the dots are not traveling down the tube. The energy is, but not the matter itself. All right? So I'm going to write that down again real fast. All right? If I say this very, very clearly with it, the dots do not travel, okay? Matter is, there's a different color. Matter does not travel, okay? All right? A wave does not carry matter. I want to make that very, very clear. All right? A wave does not carry matter. It will not travel all the way down. It obviously will move a little bit, but it shouldn't travel all the way down the tube. All right? So that's the kind of picture here. All right, so instead of crests and troughs, because we don't have a high point and a low point, what we call the parts of a longitudinal wave instead is a compression and, this is probably a new term, we say rarefaction, a rarefaction. So the compression, that area is pretty clear, obviously where the particles are very close together. The rarefaction is where they are stretching, all right? We can relate this to pressure. We don't do it too much, at least in this course for physics or AP physics. But again, obviously that would be related to a compressional wave, all right? You know, we talk about the dangers of explosions not always being the fire explosion, but that compression wave that's carried through the air has a lot of energy, and that can cause people harm a lot of times. Obviously with the soldiers and IED devices, you know, obviously those is sometimes more the scare of that compression wave than the actual explosion itself in some ways. All right. Here's again some other good pictures. All right. Now, I want to mention one other thing, and again, I apologize for this silly pen. I do not know why it's not working. I think it's all the animations. To measure the wavelength of a compression wave, not the wavelength. Okay, yeah, we'll do that first. The wavelength for a compression wave obviously would be compression to compression. Okay, compression to compression. All right. The amplitude for a compression wave will be essentially half a wavelength. Half a wavelength. The reason we say that is if we go back to basically the transverse wave, all right, if I do the distance from the crest to the trough, as we just talked about, that's not amplitude from crest down all the way down to trough. But if I take half of that, I am at the equilibrium point for that particular wave. So if you ever need to find the amplitude of a compressional longitudinal wave, it's half of the wavelength itself. All right. The other kind of silly question that you sometimes get is they sometimes go, you know, what point on the longitudinal wave is related to the crest? What we do is we say the crest is related to the compression, the rarefaction is related to the trough. We say that basically because high pressure, highest point, low pressure, lowest point. It's a little silly, but if you ever have to relate the compression and the transverse wave, they usually set it up that way. Compression with crest, rarefaction with trough. All right. We'll get to this a lot later. It's sound waves. When we really talk about a lot about sound waves. Sound waves are longitudinal waves. Sound cannot travel through a vacuum. Okay, and you can see how this works with the tuning fork. It will compress and expand the air particles, so we create those sound waves, those longitudinal sound waves. Another picture of a longitudinal wave, showing the compressions and rarefactions on a slinky. All right, and then going back and just reviewing one more time, the two types of waves, the longitudinal wave, another picture of it, the pieces of it, and then the transverse wave, again showing all the different points. It does show the equilibrium position on this one, just saying it's the middle. All right, so if we wanted to try to identify these, what type of wave would that be? 1, 2, 3, 4, 5. That's the time you get longitudinal. Okay, second one. What type of wave would this be? 1, 2, 3. It's transverse. Less time on that one. All right. What about these two? The first one's going to be longitudinal. Second one's going to be transverse. Okay. So obviously be able to identify what type of wave you have. Not too difficult. Okay. A wave can transmit what without transferring matter? That would be energy. And the shortest distance between 2 points on a wave where the wave pattern is repeated is the wavelength. Very good. I heard you all answer this. All right, so what causes the disturbance? All right, what can cause the disturbance? There's two ways to create disturbances out there. All right, one is a wave pulse. This would be a single motion, creating that wave. All right, it would be, if I do a sound, it would be ah. That would be a wave pulse of sound. All right, it's just one initial creation of that wave. All right, that would be rocking the pond, me yelling. Okay. The other example is what we call a traveling wave. This is a continuous or a regular set of regular set of pulses or basically disturbances. So this would be me talking. I'm constantly creating more and more waves. This is a traveling wave. I just keep on talking forever and ever. It's getting so tiring. All right, I keep on talking. It's not a pulse. All right, that would be a traveling wave, a continuous motion of that sound coming towards you. Obviously, this one right here, the traveling wave, if you click on that one, and it works, is, somebody doing a rope exercise where they have to keep on lifting up and down the rope and creating transverse waves on a heavy rope. All right. So this leads us to the last part of this. Let's talk about the properties of the waves. And again, some of these are characteristics as well. All right. So waves themselves, we say, have these cycles, okay? Be prepared. We don't always just say this many waves. We'll sometimes say this many cycles, this many oscillations of the waves. They're all the same thing. But frequency, we've talked about that before. Amplitude, all right? All that stuff is basically, this is where we kind of obviously relate it to simple harmonic motion again. The only new ones that we really are talking about, we've never specifically used yet, would be wavelength. Speed is not new. All right, that's not new. But wavelength would be the only thing that's kind of new here. So we already know about frequency. Okay, we already know about frequency. It's again how often the oscillations are occurring over time per second. Okay, sorry, I just want to write in one thing here. And the frequency symbol in all formulas is F. Okay, a lowercase f. That's what you'll see on the formula sheet. All right. Nothing new there. We've talked about that again in other simple harmonic motion. It is the inverse of the period. Please don't forget that. Okay. Sometimes they give you the period, which then they immediately want you to change the frequency before you use the wave equation we're about to learn. All right. Amplitude. Again, we already talked about it. It's the half the distance between the highest and lowest points, so that kind of tells us how to find the wavelength, a compression wave, and technically a transverse wave. It is related to energy. More amplitude means you will have more energy in that wave. It's a greater intensity. We're going to talk about how that relates with volume when we deal with sound. When we deal with sound. But we don't have a particular formula for this. You won't have to actually calculate out the amplitude. You might have to look at a diagram and recognize that it's the highest or low, distance from equilibrium up or down. Wavelength. This is obviously sort of new. The symbol for it is lambda, okay, or what I call the armless running man. Okay, it's kind of silly, but that is lambda. This one I've had issues. People going, how do I measure wave length? Okay, obviously length is measured in meters, so wavelength will be measured in meters. Obviously, it could be centimeters or nanometers in some cases. You're going to have to convert it always back to meters in your formula. It's again the length of one entire wave. Speed, how fast the wave is going. Nothing too special there. We'll obviously say velocity quite a bit, but since we're, this is going to be another situation just like in kinematics where we basically have that wave go only one direction. So we're not going to talk about positive and negative velocities too much. It'll be primarily what we consider speed. And so that officially leads us to the wave formula. Velocity equals frequency times wavelength. Velocity equals frequency times wavelength. All right? And so, there's really nothing too special for me to kind of explain there. I mean, it's a pretty straightforward formula, not too complicated. They will love to give you frequency. They will love to give you the period first, so convert that to frequency and then plug it in. There's all different ways that they might use this. It's something that you might have to look at the problem a little bit and go, can I figure out the frequency? Frequency is, again, number of waves per second. So you might have a diagram where you have to count how many waves are passing in 1 second on the diagram. Wavelength, you might have to look at the diagram as well. Speed, that's essentially given to you. Okay? So if I do a quick problem, if a wave has a velocity of 250 meters a second and a wavelength of 6 meters, what is the frequency of the wave? All right, I have my formula. I obviously rearrange, and that is not correct. There should be a division there. I think that's going to be in the next step. I might skip that. Ignore my error there. Okay, we're going to divide. Oh, there's all sorts of errors with this. Yikes. All right, sorry. Let me go ahead and adjust this sum. I love sharing my mistakes. Oh, of course, it's going to go away, isn't it? All right, well, I'll let you guys deal with it. So again, what we need to see here is this should be frequency equals velocity over wavelength, and then frequency would be 250 divided by 6. All right, this is so obvious to see, right? Sorry about the mistakes. It should come out to 42 hertz. 250 divided by 6 is 42 hertz. Okay. The piano string tuned to middle C vibrates with a frequency of 264 hertz, assuming the speed of sound in air is 343. Find the wavelength of the sound produced. All right, so once again, let's see if I have this right. Yes, wavelength is velocity divided by frequency. Okay, and so, oh, there's that equal sign again. 343 divided by 264 is 1.3 meters. So it turns out, it's kind of crazy to think about. That sound that you hear, its wavelength is 1.3 meters long. All right, it's longer than a meter stick. All right, but that would be your answer there. Nothing too special with the formula. I don't think you should be too tricked by that. Again, be prepared that they might obviously throw period in there. You could technically create a new formula, velocity equals wavelength times divided by the period. Most of the time, I just convert it and use the initial wave formula you see on the bottom here. All right, and so here's one more quick example. All right, where I think they give you the frequency, or they split it out. They give you the number of vibrations in 30 seconds, so you actually have to calculate the frequency, vibrations over time, all right, and then calculate how far, how long is this wave. And that is basically it. I'll talk about one other quick thing, just so we notice this, all right. Going back to this formula, velocity equals frequency times wavelength. Okay. One thing we will like to do quite a bit is we want to be able to understand the relationship between frequency and wavelength. Okay. So if I draw it out, if I go, okay, I want to draw a high frequency wave. That would be a wave that obviously has a lot of waves occurring over a period of time. Let's say this is 1 second. So how many waves pass in 1 second? I'd have to count it out. Low frequency, obviously, would be something much longer. Okay. What do you notice about the wavelength as you go from high to low frequency? What do you notice about the wavelength? Okay, pretty clear. Frequency and wavelength are inverses of each other. Frequency is inversely related with wavelength. As I increase the frequency, that means more waves are closer together. That means the wavelength is obviously less. Okay, it's not as much space between successive waves itself. So that's one thing I want to point out real quick. The other one, kind of like I mentioned early on in it, where you have to maybe identify the wave. you might have to be ready for something like this, where instead of starting in the middle and going, how many waves is this? Well, this is one wave. This is two waves. That's easy, okay? They won't always give you that. Instead, you might have to be prepared to go, all right, it starts right here and goes up. How many waves would this represent? How many waves is this? Well, this is one wave. All right, that is only one wave, and then basically this is a quarter of a wave. Okay, a quarter of a wave. So this is actually only 1 wavelengths. All right. So this might be something you're going to have to make sure you look very carefully. You're going to have to discern it and go, where do I want to start watching my wave? Where do I want to look at it? Because I get plenty of people that say, this right here is only a half of a wave. Nope, that is a full wave right there. We got to be very careful with that as well. All right, so again, we looked at mechanical versus electromagnetic waves. These waves all carry energy. Mechanical needs that energy to travel through a medium, while electromagnetic does not. We looked at whether it's transverse or longitudinal. We went through quite a bit of describing each wave in terms of crest, trough, amplitude, compression, rarefaction, amplitude. All right, and then eventually leading us to the wave equation, which will be very, very important to use, especially in AP. All right, that's it. Thank you.